Hi, hello everyone. So last time we left off with our transformation matrices, and we had our object that rotates, and this time we're going to actually doing perspective matrix. What perspective does allow us is, well, to basically change our viewport, right? Because right now our viewport is this, and we're limited to this world. And second now, so, and our viewport was usually going from -1 to 1, right? And 1 minus 1. I think that below is -1. I always reverse them, but we'll double check that. And there is also one more important information that I never even mentioned. We also have z-axis here, right? We have our depth buffer, and usually depth buffer, unlike these ones, in metal at least, it goes from 0 to 1. So what does that mean? So let's just discuss it quickly. So if I go to our shader here, and our position was usually 0, if you remember, right? So here I could just say our position.z is equal to 1, and it will render it, right? It's still rendered because it's in that limit of 0 to 1. But if I go to 0.01 and I try to render it, there is nothing, because it doesn't fall in that range of 0 to 1. So it's just something that's going to be important for this video, and I wanted to mention it quickly so that you know that device coordinates for metal, so it's not the same. Some graphics APIs are a bit different, but each one of them has -1 to 1, but the buffer sometimes is a bit different, and in metal it goes from 0 to 1, right? So if your z is not in that range, it will not be rendered. Okay, so with that said, let's start with code for our camera, and then we're going to look at what camera are we going to do. And for that we can just go to our shader where we already are, and here I'm just going to say constant pect, sorry, not pect, it's just float 4 times 4. So we're going to say perspective. I'm going to say view. We're not going to cover view camera yet, but just for the future, because obviously we will have that. And then we can say here, and I have to place comma here, and I will just say perspective view times this. Good. Then in our unlit render pipeline, and actually it's not going to be part of render pipeline, it's something that we're going to pass in because it's going to be later part of the camera setup, not for now. Perspective view buffer, and it's going to be of type constant buffer, and it's going to take, what was this in the float 4x4 represent our matrix. So I'm just going to do this so that it's a bit more readable, and then we just need to paste it like usually. So I'm just going to copy paste this line. Our index was 5, right, if you remember, and here we're pasting perspective view buffer, and then we just need to create it. And if I create it somewhere over here, perspective view buffer is of type constant buffer, so Cindy float 4x4, and then we just need to initialize it. So we're going to need our matrix, so let's just say perspective view, and by default we're just going to use identity for now. So we're going to cover this, and then we just need to write to that perspective view buffer, not write, what are we writing, that perspective view matrix, not camera matrix, and then we need to paste it. And I probably need to unwrap it. No, maybe yes. I don't even know anymore. It might not build. Why? Aha, it's a late constant. It needs to be var, and I think we're good. Let's just check it. build failed, coordinator has no initializers. It actually needs to be nil because it's not in the constructor, so that means let's change it to nil, and let's say here unwrap operator. Still it needs to be unwrapped, but I haven't created it. Sorry about this. I usually don't use Swift that much, to be honest, so but I think we're good now. Almost. Device, unwrap it as well, and finally we're good. Okay, cool. So just to quickly discuss orthographic projection. So basically it's a projection on our plane, and the orthographic one is kind of parallel one. So you're not going to see, if you take a look here, we have perspective, and let me just get rid of this quickly. We have perspective where you can see kind of like Z is projected, and it's usually done for 3D games. And orthographics, it can be used for 3D games, but like for isometric games, and here we're just going to use it to basically map our space a bit differently. And then when we have 3D objects, we might return to it as well. But as you can see here, it just projects it like a 2D. Even if you were to rotate it, it will still be kind of 2D-ish a bit. You will see in the future what I mean, but right now I'm just going to use it basically for remapping our coordinates. And you can also see it here, right? Here it kind of has this, if you take a look at the spheres here, maybe I can somehow zoom in. No, I cannot for some reason, but they're kind of same size, even if distance between them is kind of different. So you don't have like this depth perception with the orthographic camera of a distance, like you would, for example, with the perspective projection. But enough with that. Our purpose and what we're going to use it for is actually, so previously we had this -1 space, but now let's say that we're working on 2D game and we want to have space that goes from 0 to 800 maybe. So we need to learn how to do that, and we can use this orthographic projection for that and orthographic camera. So let's get started with it. Okay, so let's try to imagine our orthographic projection here. So I mentioned that we have, for example, world. So let's imagine that this ugly rectangle is our screen that goes from -1 to 1, and we have 1 here and -1 here. It also has depth, which goes from 0 to 1, but that's not important right now. So let's say that we want our world to scale to 10 and -10 instead. So we're going to use these units, right? -10 and 10, but we still need to map that to -1 to 1 space, right? So how do we do that? Well, let's say that we have our world, and let's say here is -10 and here is 10. So how can we map it to this space -1 to 1? Well, we just need to know the size of our world, right? So we have right side and we have left side. So our world size is, and bear with me here, it's just right minus left, all right? And since here our world of metal, right, metal world, metal coordinates go from -1 to 1, it's 2 units, so we can just say 2x, and x can be anything here. We just say 2x over right minus left, which is which just gives us the scale of our world, right, from left to right, and that's it. And that's already solves a big part of this projection. But you can also think about the orthographic camera as a mapping from one space to another. We had -1 here, right, 1 here, and we just wanted to map to -10 to 10 space. And later we're going to see how can we move this around, because this is just scaling, right? We just can scale left and right, but we cannot move it. We cannot do yet, for example, we cannot do space that goes from 0 to 20. We're going to cover that a bit later, but this is already good enough for what I'm going to show you. So let's code it, and that's actually really easy to do. So I mentioned that we have to multiply x, right? If you remember from our matrices, orthographic. So let's just say, let's just finish this. So we're going to have left, we're going to have right float, we're going to have bottom of type float, we're going to have top of type float, and then we're going to have near of type float. This is for z, and we're going to have far of type float. Then what we're going to do is we're going to just return this here. And already a tip, you can see for example scale matrix, and if you remember, right, our x coordinate of our vector is multiplied by this, right? If you know matrix, and we discussed this last time, and we're covering matrices. If we have, let's say we have our vector x, y, z, and then we have this, right? So x was multiplied by this member, then this, and let's say 0 here, right? X gets multiplied by this, y gets multiplied by this, blah, and then we get x, right? And for y it was here was nothing, here was y, nothing, right? And then when we do multiplication, y is multiplied by this. So it's kind of like a scale matrix. So this part of what we're going to do is sort of similar to scale matrix, and it's sometimes called scale part, because it actually, right, as I mentioned, we were discussing scale when I was showing the drawing. So let's here just say let r0 c0 is equal, and what did I draw here? Like, what did I say? I said 2 over, right, minus L, and our x is in our vector, right? So our x is in vector, and so we just need 2 and then right minus left, 2 over right minus left. So let's just code it. Let's just say 2 and then right minus left, and same is actually going to be true for y. So that's going to be here, top minus bottom, and for z it's a bit different because z is going from 0 to 1, so it's not 2 over, it's actually 1 over. So let's just do that, 1 over. So here just far minus near, and we can place those here. So this one goes here, and that's it, right? You probably already figured this one out. Row 0, column 0. I'm just indexing from 0 because that's programming for you. Then there are complaints about, I just need to say this, float 4x4, and I think we're good. So let's just test it out. Let's test it out now. So in our coordinator here, let's just say orthographic. So let's go minus 10 or minus 5. 10 is quite big. Minus 5 at bottom, 5, and let's just go 5 as well. So let's test it out. So testing part. Okay, you can see this is already smaller. I'm just going to do one change because this would be very annoying. You don't have to do this if you don't want, but I'm just going to set our text down to 1, 1, and I'm going to get rid of this rotation part. I'm just going to say we're going to use translation for now, 0, 0, 0. So it should be at our center, but now it's way smaller, right? Why is it smaller? Well, because let's clear this out. Because right now this has width of 1 unit, and here it's -5 now, and here it's 5, because we defined it like that, right? If I was to say, okay, I'm going to move this to coordinate, right, and our coordinate is in center, I could say, okay, let's move it to something like -4.5, and then we can just leave y here, and then it's going to be something like this. All right, let's just test it out, because we have to test it as well. So what did I mention? -4.5, and it is here. If I was to say, okay, it's going to be -4.5 or 4.5, it's going to be somewhere at the upper left corner, right? Because it's almost at 5. Okay, if I put 5 here, it should be visible because it's right at the edge, right? Because we defined our far coordinate as 5. But as soon as I put here 5.01, we should not be able to see it because our far coordinates. Okay, we do see it. That's a bit weird. That's a bit weird. I think I missed something. Let's just see. 6. Is it visible? I think I'm overriding in its shader. I forgot to remove it. No? Okay, maybe I just created a bug here. It should be simple to resolve. So let's see our matrix. Far, near, I mentioned 0 and 1. So 1 over far minus near. To C2. Is translation matrix wrong? Maybe I had a bug from last time or something like that. Translate. I did actually. It's not Z here, it was Y. Because I am quite sure that this math needs to check out. And it does now. So it was just a bug from last time. Okay, be sure to fix that. 5.5 will work, 6 doesn't. Okay, I'm just going to be confident and say that 5.01 doesn't work. Oh, well, let's just check it anyway. Yeah, it doesn't work. Yeah, that's perfect. So our far plane is 5. Perfect. All right, that covers this scaling part of matrix. So we have also translate part of matrix if we want to move it not to be in -10 to 10, because right now we can just scale. But let's say that we want to put it at 0 to 20. So we have to cover that as well. So let me see. So we have solved this problem of scale, but now I just want to translate it as well. So we had so our problem is we have our space which is -1 to 1, right? We could scale it to -10 to 10. Let's say we can scale it, but we cannot move it to 0 to 20 yet. So we're going to cover that part, and I'm not going to do it visually, I'm going to do it a bit differently. So I'm just going to use algebra, basic algebra to get to it. And so we can write something like our left side is either equal or less than x, and x is our equal or less than right side. So we just need to solve this. And how can we solve this? Well, first of all, we need to have -1 here. So this is what we need, right? So what are we going to do here? So let's get rid of this L. So we can just subtract everything by L. This becomes 0, right? L minus L is 0, x minus L, and then we had right side minus left side. Okay, then we can write this as 1 here, right? So if I write this like this, and then it becomes 1, but I need to do same here, right? And I need to do same here, but 0 divided by anything is 0, right? So it's not that important. So I'm just going to write it for clarity here. So we had x minus left side, and then we had right minus left side here, and it's less or equal to 1. So next step that we can do is we can scale it to actually be in space 0 to 2. So 0 times 2 is 0, and this is x minus l, right, minus l times 2, right? Then it's less or equal to 2, because we also have to multiply this side by 2. Okay, we're almost there. It's not that hard now. So we just need to move it now to -1 to 1 space. We want to do that. So this is 0 or -1. It becomes -1, right? So we can just rewrite this part. And then -1, right? And then it's less or equal to 1, because, right, we did this, and we did 0 minus 1 here. Okay, all right. So we're almost there. Let's see further. Further, what we can do is we're just going to rewrite this. We will rewrite this up as well. Right minus L. But we can rewrite this one as right minus left side, right minus left side, right? This is just 1. Okay, and then we can solve for it. So we can say -1 is less or equal to right minus left. So we had 2x minus 2l minus. So now this is just right plus left, and less or equal to 1. So we can solve for that as well. So 2l plus l is negative l. We're just left with l. So we can write it sort of like this. Let's just go further down. So we had -1. So we can pull this 2x out. So we have 2x right side minus left side, and then we're going to have minus, right? So this is our right side. So let's do it like this, minus, so it's going to be right side plus left side, right? Because this is minus L, and because this is negative, right? So I think this should be correct. Let me just double check here, because I hate this pen that I'm using. So we had here, we move this out. We had, let's just move here, minus L. So we move this to 2x, right, minus L. And then we had minus R, minus, then R becomes the positive. And the side of L changes to positive, right? Okay, it's correct. So I'm just going to rewrite this because it's super ugly, but basically we solved it, right? We have -1, then we have 2x minus, and you can already see this whole term is already familiar, right? 2x right minus L is already familiar, right? Because I already mentioned it before when I was doing this drawing, and it's this part is already solved, right? So if I was to look at our matrix, and we have it right here, 2 over right minus left. So now we solved, now we have a proof that this is correct. But we also, if I was to look here, we also have this part minus right side plus left side over right minus left side, which is transform part of our matrix. So basically, if you remember, right, so we had our matrix. So this guy is in this part of the matrix, right? It goes over here for x. And this part is translation part. Sorry, if I could manage this, and it goes to this part. So let's say we had our scale 0, 0, and then translate part. And the same applies for y, right? We have scale part for y. I'm just going to say scale x, scale y, then translate x, and then translate y as well. And then here scale z, translate z. Anyway, you get the idea. So let's just solve for that. Actually, not solve. We need to add it to our orthographic camera. So sorry about this. So let's just say L is, now we're in row 3, C0. So what was it? How did I solve it? So it was minus right plus left over right minus left. So let's just add it. Minus right plus left over right minus left. If I'm not mistaken, I'm not. Good. Good. Let's see. Then for y it's going to be very similar. Minus top plus bottom over top minus bottom. And then for z it's a bit different, and I would encourage you to solve it, maybe yourself. But it's a bit different because we're mapping to 0 to 1, not minus 1 to 1. And here, let me just check how did I solve it. I'm not going to do it all over again, so I do encourage you to try to do it. But it should be, at the end, it should be minus near over far minus near. And then we can just use them here. So R3, C0. And I think we're good here. We're good here. Something here it's complaining. Fix. So if I was to change this to 0, let's say 10, 0, 10, and this will not, we will see nothing at screen now, right? Because we're at minus 4.5. That's correct. But if I was to change it to, let's say, 0.5, and here I'm just going to use 0 because, yeah, why not? Okay, we see it here. Because we moved, right? So now our space is here it's 0, here it's 10, and here it's 0, here it's 10. So we cannot just use 0 here. If we want to be in the middle, if we want to be at the middle, we have to use 5, right? Because we're in space 0 to 10. Okay, and we are. All right, so let's just see if our z works as well. So if we are at 6, we're not going to see anything. Right, that's correct. If we're at 5, we should still see it because we're in correct space. All right, that's it. It's there. And if I was to place 5, 5, this z can be at 0, but 5, 5 should place us at the center. Yeah, it does. Yeah, so cool. So now you can use this orthographic projection. I also just like to call it mapping from one space to another. So it's sort of like mapping, you're mapping from -1 to 1 to some other space. So you can also think like that about it. And that's the way I usually think about it. But yeah. Hopefully you enjoyed this video. If you enjoyed it, please like, subscribe, and hopefully this is all clear. It's not that hard. Like when you're trying to learn all this graphic stuff, you get lost with orthographic camera. How does it work? Why it works like this? And this is really simple explanation. It's just some small algebra that allows us to represent any space that we want here. So that's it for this video. Please like, subscribe, and until next time.